Okay, here is the lesson that's recapping very quickly Hooke's law and then moving on to stress and strain. Stress and strain, moving from something which is very dimension dependent into something which is dimensionless dependent. It's material dependent, which is much more useful to engineers. Okay, a quick recap of Hooke's law. F equals kx. The force required to cause an extension is directly proportional, and k is known as the spring constant. That gives rise to a graph, which is a force extension graph, which is directly proportional up until a point of the elastic limit, and then it starts to roll off. We'll talk more about these limits in this zone later on. And also, we should say that usually you might see an extension force graph in that orientation, because this is our independent variable and that is our dependent variable. However, I prefer this style because the gradient gives me the spring constant directly. Okay, so I'm not going to go through all of that. However, I will jump to the idea that if that something that sits like that would be a stiffer spring, and something that sits like this would be a weaker spring. What do I mean by stiffer or weaker? Well, we've obviously got the stiffer or weaker as in the makeup of the spring, but this was also achieved by having, I'm sure we could do this, we had two in parallel. Now I'd like you to think of the two in parallel as having 2 times the area, as opposed to a normal area. And what we were looking at, those that had 2 times the area, if the same force were applied, then you would get the change, the extension for the 2A would be less than the extension for 1A. In other words, this would extend more than this one. And if I did a similar thing as well, and we placed those springs in series compared to just one spring on its own, and you applied the same force, then the extension of twice the length was actually greater than the extension of just one length. So really what this is saying is that dimensions matter. If something is thicker, it's not going to extend as much because it has a greater cross-sectional area. If something is longer, though it may be the same material, the extension will be greater because it's twice the original length, or it's a longer original length. So there's no point in having lots and lots of tables that have every dimension under the world. What you want is we're looking for dimensionless properties. And that would mean you would have something for steel, and you could work out what the extension would be given a certain area, rather than having to reference every area or every length. So the way that we go about this, that's a quick recap on Hooke's law. The way that we go about this is, rather than the force, we look at the stress. And the stress is the force divided by the cross-sectional area. I suppose I should be calling this cross-sectional area. Some examples love you using that term rather than just the area. Okay, good. So force is of course measured in newtons. So this top bit's measured in newtons, the bottom bit's measured in meters squared. So therefore the stress should be measured in meters squared. or more usually it's measured in pascals. Good. So in this instance, if you're looking for the same extension in two objects, like we did before, the thick or the thin one, but you're looking for the same extension, then for this one you would require twice the force, but it has twice the area. This one you would have one single force, you'd have the normal amount of force because it has the normal amount of area. So if you see, the stress for both of these objects remains the same. So it's dimension independent. So that's why stress is so useful. What about the strain? Well, rather than extension, we talk about the strain, and the strain is defined by the extension divided by the original length. Good. Once again, we have a long spring or piece of wire and a short piece of wire. In order to achieve the same force, if we apply the same force, so the same force applied, then this one would stretch, the delta x would be twice as much as this one. However, you have twice the starting length as this one. So if you divide the two, you get delta x over L. The same thing is achieved when you work out the strain, so the same strain. So once again, it's dimensionless. So let me just write that down again then. So stress is force over area. Strain is extension over original length. I'm not quite sure of the symbols they give, but force, let's go force over area. Let's go extension over original length. It's probably worth noting here that if this extension's in meters and the original length is in meters, then actually this is a dimensionless property of the strain. Okay, last thing, however, would be that if I were to plot nowadays the stresses and the strains, then by comparison, the gradient I would get is no longer the spring constant, it's called Young's modulus. In other words, it is the stress divided by the strain. Force over area, x over L, which is actually FL over XA. And I'll just call that YM, or some people call it big E, Young's modulus. And this has the unit, of course, because the strain is dimensionless. It has the same unit as the stress, which is newtons per meter squared, or pascals, just as the stress did. Okay, so there in our comparison is over K is E, spring constant, equals Young's modulus. Every time you think of stress, think of the force. Every time you think of strain, think of the extension. Every time you think of spring constant, think of Young's modulus. Time for some questions. Right, steel has a Young's modulus of 2 times 10 to the 11 pascals, or newtons per meter squared. If there was original length of 2.75 meters, and the cross-sectional area, we don't know that, the diameter is 1 millimeter, what would be the extension if 1 kilogram were suspended on it? Good, okay, right, so how do we do that? What's the extension if 1 kilogram is on it? Good, let's write down Young's modulus is stress over strain. That gives me force over area, extension over original length, or force times length, such as that. Good. Bear in mind that the force here, what's the force? It's not 1 kilogram, but it's the weight, which is mg. And what's the area here? Well, that's the diameter. So we're looking for pi diameter divided by 2 to give us the radius squared. Let's plug it all in then. So 1 times 9.81, giving us the weight, by the original length 2.75, all divided by the extension, which is unknown. So let me put the extension up there in Young's modulus down there. So let's put in Young's modulus 2 times 10 to the 11 by pi. We are 1 millimetre, so that's 1 times 10 to the minus 3 metres, divided by 2, square that up. And that gives me my delta x, which is, I believe, 1.7 times 10 to the minus 4 metres, which sounds about right. 1 kilogram on steel is going to stretch 0.1 of a millimetre. Okay, let's try another one. Let's take some aluminium this time. See whether you can do this. Aluminium has a Young's modulus of 0.7 times 10 to the 11 Newton metre squared. I've just used that unit, though they are identical. The top unit, pascals Newton per metre squared. And I have some wire with an area of 4 millimetres squared. Have a length of 140 centimetres. And I want to know the force required in order to stretch it, to stretch by 0.5 centimetres. Okay, let's see if you've got all the data. You've got Young's modulus, you've got an area, a force, a length, and you want to know the force. Okay, if you think you know how to do it, press pause. Otherwise, here comes the answer. Okay, so Young's modulus is, I'll make the shortcut here, and we're looking for the force required, so that becomes EXA over L, which is Young's modulus 0.7 times 10 to the 11. The extension is 0.5 in centimetres, convert it into metres. Multiply that by the area, which is 4 millimetres squared. So how do you change millimetre squared into metre squared? I'd suggest it is as simple as saying 1 millimetre by 1 millimetre. Multiply that together gives you 1 millimetre squared, which is the same as saying 10 to the minus 3 multiplied by 10 to the minus 3, which gives us 10 to the minus 6. So 4 over 1,000 squared divided by an original length of 1.4 metres. Remember, I had to change it out of centimetres into 1.4. And that gives us a force of, might have to use my calculator for this one, 0.7 xp11 by 0.5 by 100 by 4 divided by L. The force required is something in the order of 1 times 10 to the 5 newtons. Okay, good. So once again, this is quite straightforward, but it's just a lot of careful entering of values into this equation here for Young's modulus. let's try one other idea, because we dealt with the force, so we looked at the force analogy, we've looked at the extension analogy, we've looked at the spring constant analogy, and now we need to look at the energy, or the work done. Let's just remind ourselves: force, extension, spring constant K, the gradient is K, the area, which is in effect the force, the average force times the extension, which is a half, Fx, actually gives us the work done, or a half kx squared if we substitute our expression F equals kx in for F. Okay, so our expression for energy is that. So coming back down to Young's modulus, stress, strain, the analogies, Young's modulus, energy, gradient, area. And the area is the stress, the average stress, times the strain. Because, of course, this is changing, like that's changing. So we want to find an average stress and multiply it by the strain, therefore giving us the whole area, like we did up here, where we were looking for a half F, because that would give us the equivalent of the entire area, given a triangle. So this gives us a half F over A by X over L. That's the same as a half Fx over area by volume. So this gives us the work done per unit volume is a half stress strain, because that is half work done over volume. So energy per unit volume is given by the area under the graph. So the area under the graph is the energy stored per unit volume. Good, and let's do an example of that, shall we? Let's leave that there. So we might say to ourselves, let's go back to the aluminium one. 0.7 times 10 to the 11 Young's modulus. Let's imagine that was, it was in the previous question. Just find it somewhere. Probably on the other side. Oh, there it was. Let's just regurgitate that. 140 centimetres and 4 millimetres squared. And now, what is the work done in stretching 0.5 centimetres? The work done in stretching 0.5 centimetres. I think all the information there is that we needed. Just be absolutely sure. Okay, so what do we do? Let's go from scratch again. The work done in stretching. So probably what's best is to work out the force and then work out the force times the extension, giving us the work done. Good, so we're going through much like we did before. Okay, Young's modulus is force over area and x over L. F is therefore EAX over L, but that's the force required to create that extension. I'm looking for, so in other words, that would be the force needed in order to get to X. But I'm looking for the average force in order to work out X. So I really need to say that, therefore, F bar is a half EAX over L. So F is going to be, I'm going to use some of the figures from last time round. It's going to be a half by 0.7 times 10 to the 11 by 4 times 10 to the minus 6. Remember the conversion by the extension 0.5. Did I say centimetres? Yes. So divide that by 100. Conversion, of course. Divide the whole thing by the original length 1.4 gives us, and the half, 500 newtons. The average force exerted. It starts at 0, it finishes at 1,000. The average force is 500. Okay, so now the work done in stretching it will surely be the force by the extension, which gives us 500 by 0.5 over 100, giving us 2.5 joules. Okay, good. So, yes, I think that's all the examples you need. I hope that makes sense. Done.